right, guys, today we're going to be taking a look at domain and range still, but we're going to be focusing in on discrete versus continuous graphs. So these are two new vocabulary words that we'll be learning today. So discrete versus continuous graphs is the title of our notes. You'll see two graphs to start off with right underneath here. You'll notice that they look very different. The one on the left here has a lot of dots or points that go across the graph, and the one to the right has a constant line that goes across the graph. So we're going to start off by listing the domain and range of each of those. Now you'll remember from yesterday that domain deals with our x values and range deals with our y values. That is still going to remain the same today. Now, I know it's a little out of order, but we're going to go to this right graph and find the domain and range of this graph first. When we're writing the domain of this graph, we are going to write our inequality. And just like yesterday, I would encourage you to take a highlighter and highlight the x-axis, still the horizontal axis, even though it's representing time here. And I want you to highlight where the x's begin on the left side and where they end on the right side. That gives you a nice visual for what our x values are stuck in between. Remember, the smallest x value goes on the left-hand side, and the largest, or the furthest right x value goes on the right side. Our smallest x value that this graph hits is over here at 0. Now, we can assume, because it actually touches it and it doesn't form an obvious open point, that it includes it, so we'll put a line underneath. The largest x value, as you travel along, it includes all of these x values, and then it stops right about here at, we'll say, 46. Because it touches there and is not an obvious open point or an arrow, we'll put a line underneath it. Now, I want to be clear about this inequality. This inequality is saying that x can be any number, whole, fraction, decimal, it doesn't matter what, any number in between 0 and 46. Because it is a line, it includes all of those pieces. Let's check out the y values and talk about our range. Remember, the only difference when you write your inequality for your range is you put a y in between. We'll still start with that our y is bigger than something but smaller than something else. And just like with domain, you'll put your smallest y on the left, your largest y on the right. Take your highlighter and highlight the lowest y value that the graph takes on. It includes all these y values up until right there. So our lowest down, our smallest y value that the graph takes on, you should recognize this point on the y-axis as 0. It includes it, so we put a line underneath, and then it travels all the way up to this top point, right in between 90 and 120, which is 105. Put a line underneath that as well, because all of these points right here that reach 105 are solid points. So on this right side, we call this graph a continuous graph. It's continuous for obvious reasons. There's no breaking point. It's a solid line. As it travels all across the graph, it is continuous. When you have a continuous graph, you'll notice that our domain and range are written with inequalities. Now let's go over to this left graph and take a look. On this left graph, you'll notice that we still have a coordinate plane. We're still on an x and y axis, and we're still going to find the domain and the range. We have our x-axis, we have our y-axis, we can find our domain and our range, but it is not continuous in that there's not a line in between everything. You can think of, this is called a discrete graph, by the way. The way I remember a discrete graph is dots. It looks like a bunch of dots across the page. When you're writing the domain of a discrete graph, you are not going to use an inequality like we did on the right, because an inequality says that it includes every single number in between, for example, on the right, 0 and 46. In this case, It is only specific X values that are included. So when we write our domain, we're going to use a bracket and we're going to list each individual X value that is included by our points. So when we look at this first point, we have an X value of 0. The next point, we have an X value of 1. The next point is an X value of 2, and so on all the way up to 10. We do not use an inequality because it does not include any of the fractions and decimals in between 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It only includes those specific values. So that's our domain. Let's check out our range. Remember our range, we're looking at the y-axis. The first y value that the graph takes on is 0. And then what's right in between 0 and 20, this point is at 10. Then 20, all the way up to 100. So the main thing I want you to understand here is that when you're finding the domain and range of discrete and continuous graphs, they're going to look different. So discrete graphs look like a list of ordered a list of numbers when you're finding the domain, like this and like this, whereas a domain and range of a continuous graph are going to be written as inequalities. So let's sum that up down below when we where we have these words discrete and continuous. So a discrete graph, remember, looks like a bunch of points, and the domain and range are distinct values. In other words, we just list them out. You need to write list in here to help you remember that. On the other hand, if we want to be talking about the domain and range of a continuous graph, we write the domain and range as inequalities. Because it is a continuous line, it includes every single number in between all the whole numbers. We're going to work with that for the remainder of the notes today. In the example beneath those graphs, you'll see a little word problem that we're going to work through. Very basic. We're given this scenario. Tickets for a soccer game cost $2 each. We're going to write a function to describe this scenario. So if we want to find the cost of the soccer game, f of x, or how much money is going to be made at the soccer game, it's going to be 2 times the number of tickets that are bought. So our function is f of x equals 2x. I want y'all to think what's driving the change. What's driving the change in the cost of the soccer game? That is always our x value. So think about what this x variable represents. That x variable represents the number of tickets bought. The number of tickets that are bought is going to affect the output, f of x, which in this case would be the total cost. Let's now fill in a table to describe, to demonstrate what's happening here. If you bought 1 ticket, how much would it cost? Your y value would equal 2. If you plug 1 into that spot, 2 times 1 would give you 2. If you plug 2 in, if you bought 2 tickets, 4. If you bought 3 tickets, 3 times 2 is 6. If you bought 4 tickets, 4 times 2 is 8, 10, 12, 14, and so on. If we're going to now graph that function, I want you first to label your axis. So think what our x value represented up here. Our input represented the number of tickets we bought. That affected the y value, and the y value was our total cost. So let's fill in some values here. If we bought 0 tickets, it would cost $0. If you bought one ticket, it would cost $2. 2 would cost 4, 3 would cost 6, and so on. Now I want you to think for a second whether we should connect those points or not. Would it make sense to include a line to connect all these? If we included a line, it's saying that every point on that graph is possible. Is it possible to buy a half a ticket? Is it possible to buy 3 3/4 tickets? You should be thinking no. So I want you to make sure that off to the side, you're making a point. Do not connect points. If you need to make a note why, you cannot buy part of a ticket. So given that's the case, is this function that we see here discrete or continuous? Since we're not connecting the points, and since it's just dots or points across the page, distinct points, we would say that it is discrete. And again, how do we know? It's the same reasoning that we wrote up there. You cannot buy part of a ticket. Now, keep in mind when we're listing our domain and range, how we found our domain and range of the graphs above. When we found our domain of a discrete graph, we just listed the specific x values. So we're going to do that when we find domain and range in this piece. So our domain, we're just going to open up our bracket. You can buy 0 tickets, 1 tickets, 2, 3, 4, 5, and so on. Our range, what our y values can be. Again, we're going to just list off the distinct points that can be our cost. So if you bought 0 tickets, it would cost 0. 1 ticket, 2. 2 tickets, 4. And so on. Key idea, do not use an inequality when you're talking about a discrete graph. Let's go to the next page. The first one we're going to start out with, we're going to try to write a function for this scenario that's right beneath there. Write a function describing that cheddar cheese is for sale at $3 per pound. So the total cost of the cheese is $3 per pound. The independent variable x we're going to find, and the dependent variable y we're going to find. Take a second and try to write those on your own. The independent variable is the thing that's driving the change. That's our x value, and that is the number of pounds of cheese. The y value is the thing that's affected by the number of pounds of cheese. The number of pounds of cheese that you buy is going to affect the total cost. Now let's fill in a table. Another way of representing the function. If we buy 1 pound of cheese, it's going to cost $3. 2 pounds of cheese, plug in 2 for x, you get 6. If you buy 3 pounds of cheese, 9, and so on. On our graph to the right, let's go ahead and try graphing what's happening here. Remember to label your axis. So we have the number of pounds of cheese on the x-axis, and on the y-axis, you should have that's affecting the total cost. You can buy 0 pounds of cheese, it would cost $0. 1 pound would cost $3, 2 would cost 6, 3 would cost 9, and so on. Similar to the problem before, I want you to think whether you should be connecting these points or not. I don't know how much y'all grocery shop. Maybe you go to candy shops more often, but is it possible to buy a part of a pound of cheese or of candy or of ham or of anything that you buy by weight? The answer is yes. So in this case, we would connect the points. You can buy 1.5 pounds of cheese. You can buy 2.6 pounds of cheese. it is okay. It's not just sold by the exact pound. So in this case, since we connected the points, if we're trying to write what our, whether it's discrete or continuous, because we're connecting the points, we would say that this is continuous. Reason being, you can buy part of a pound of cheese. When we're writing the domain and the range here, we're going to write it as inequalities because we're talking about a continuous graph. The smallest amount of cheese that you can buy, well, you can't go negative. The smallest amount that you can buy is 0, and it includes it. And there's really no limit on the amount of cheese that you can buy. So if there's no limit, if you can buy more and more pounds of cheese, if it goes toward the positive numbers, we call that infinity. That's going to affect our range, our cost of cheese. So if you need to look back up at the graph up here, the range, our y values, the lowest cost is going to be 0, inclusive. And then as you buy more and more cheese, it's going to go up and up and up toward infinity. In this last portion here, we're just going to practice determining whether it's discrete or continuous. It's not going to be in any sort of word problem. And we're going to then write the domain and range. Key idea, remember that if it's discrete, we just list the points, versus if it's continuous, we use an inequality. So if we zoom in on this first one, we first need to figure out if it's discrete or continuous. Is it dots or not? Obviously, it's a connected set of points, so we would call this continuous, which means our domain, we're going to write with an inequality, and our range, we're going to write with an inequality. Just like yesterday, when we were finding the domain and range, go to your graph, highlight the X part of the graph that's used, and highlight the Y part of the graph that's used. Smallest x goes on the left. So if we're looking at our x-axis in pink here, you'll notice that the graph doesn't actually stop at this point. Because there's an arrow at the end, we can imagine it's going forever to the left. Think to yourself, what do we call those numbers that go forever to the left? Forever to the left is negative infinity, so that has to go on the left-hand side. No line should go underneath your inequality. Then it includes all the numbers from negative infinity up until the x value that it stops at is 4. Because it's a solid dot at 4 or point at 4, you should use a line underneath. The range, on the other hand, that's where I highlighted it in blue on the y-axis. The smallest y value is right here on the y-axis, which is a y value of 0. It includes it. Because if you travel over to the graph right here, it's a solid dot. And then it doesn't just stop right here. You can see that it has an arrow on the end, and while that looks like it's going left, it's also going forever up, so it's going toward infinity. Try the one right to the right of it. Determine if it's discrete or continuous, and then find the domain and range. Again, this is an example of a continuous graph because it is a solid line with lots of points connected. When we write the domain of a continuous graph, you should use an inequality. The domain, I highlighted the part in pink to represent your x-axis. The smallest x value that the graph takes on, you should have found was -5. It includes it all the way up to +6. It does not include it because it is an open circle there. In terms of the range, I highlighted it in blue on the y-axis, all the values that are included in our range. The lowest value down here is -6. It includes it, and then it travels up and up and up and up and up all the way to the top of the graph at +2, where it stops. It includes that +2. Those are your two examples for continuous functions. Let's look at this guy down here. You'll notice that this is just a bunch of points across the page. This is an example of a discrete graph, which means that you should be thinking we are not going to use an inequality. We are just going to list the x values that are used. So at each point, we want to list what each x value is. At the point on the far left, you'll go from left to right. That x value for that point is -2. At the next x value, that x value at that point is 0. The next one is positive 2. And the last x value you should get is positive 3. Do the same thing for the y values. Make sure you're looking at the y-axis. So I'm going to look at this bottom point, look at the y-axis for each of these. The smallest y value that the graph takes on is negative 1. The next one is at 1. The next one's at 2. And last, at this top point, that y value is 3. Practice the same thing for this far right example. I'll give you all a second to fill in each of the 3 pieces. Let's check and see how you did. Remember, the domain is what our x values can be, so we're just going to list off the specific x values of each of these points. I drew little lines down so we could understand that this first point is at 1, second point's at 3, then 4, and then 6. We'll list them out the same way when we're talking about the range. So we want to start at the lowest. The lowest value that the graph takes on is negative 2, then positive 2, and both of those top points are at positive 5. That's the domain and range of that discrete graph. Check yourself before you go on. Remember to log back into office hours if you have any questions on anything. I would love to help you. Otherwise, start your assignment. Make sure you're turning those notes and homework in.